We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
The Apollo program fulfilled the challenge put forward by President Kennedy to put a man on the moon by the end of the 60s. With this grand gesture, the U.S. became the predominant force in space, winning the space race with the Soviet Union. But Apollo was a ballistic capsule system, chosen because it was the quickest and most expedient way. The capsule would re-enter the atmosphere and tumble to a splashdown in the Pacific Ocean. Many felt this a rather inelegant way to return from space when prototypes existed of a vehicle able to be piloted back to Earth for a safe and accurate landing on a conventional runway. Test pilot Jerry Gentry.
The objective was to have a vehicle that would come back and could not only land on land, but also could be reusable, because the capsules, Mercury, Gemini, Apollo, were, once they hit the salt water and got corroded, I mean, that was the end of them. And also, there were a great many of us, especially those of us in the Air Force, to question the need or the desire to have a Navy flotilla out there to try and pick you up. It's just also to a pilot, the idea of coming down in a parachute. Most of us think the parachutes are for emergency procedures and emergency landings only, rather than a routine way of coming back to land on terra firma.
The Apollo program taught us much, but the capsule was not the answer for the future. During hypersonic acceleration and re-entry, aircraft with sharp protruding wings and fins would be burnt up. However, blunt bodies like conical capsules are very efficient, deflecting shock waves and heat away. During the early 50s, researchers started testing half-cone shapes, called lifting bodies. With rounded bottoms and flat tops acting like a wing, the body of the aircraft produced its own lift. In 1962, this V8-powered Pontiac was a familiar sight at Edwards Air Force Base. In tow was one of the strangest looking aircraft ever seen. This flying bathtub was the M2F1. Without official sanction and with little money, a group of NASA scientists independently built the plywood glider to see if a lifting body could be successfully flown. After getting a feel for the aircraft behind the Pontiac, the next step was to tow the aircraft to altitude by C-47 and test handling qualities and landings. NASA test pilot and veteran of the X-15 program, Milt Thompson, made the first glide flight in a lifting body on August 16, 1963. Although it exhibited a disturbing tendency to roll if it hit any turbulence, it proved a fairly flyable aircraft. Thompson's X-15 experience contributed much, as the M2F1 displayed quite similar approach characteristics. The M2F1 flew over 100 times, providing valuable data and demonstrating that steep power-off landings could be safe and very accurate. By 1966, with the success of the M2F1, NASA and the Air Force sanctioned a rocket-powered lifting body. The Northrop M2F2 was to be launched mid-air from a B-52. Jerry Gentry was to fly the M2F2 for the Air Force.
As you get a marvelous view, maybe you can understand what a bomb might feel like being carried aloft if a bomb had any feelings. But that's exactly what you are. The only thing that is different in our case was that we could get off anytime we wanted. And it was a long ride. It was about 45 minutes to 45,000 feet, so you had a lot of time to think about it and mentally prepare yourself for the flight.
As they reached 45,000 feet at 450 miles per hour, the little aircraft dropped away. Pilots found the experience of flight without wings only a little disturbing at first.
Once you get past the fact that it doesn't have any wings, you know it's going to lift. Anything will lift. Barn doors will lift if you can figure out how to control them, and that's essentially with the control surfaces and fins on the lifting body, we felt we could control it. The question was how stable was it going to be and how easy was it going to be to fly.
Control and stability was a problem on the very first flight in July 1966, when Milt Thompson encountered the same instability he'd experienced in the M2F1. But the flight ended in a successful landing. However, during flight number 16, NASA pilot Bruce Peterson wasn't so lucky. The same problem cropped up again, and Peterson struggled to control the rolling aircraft. He succeeded, but after dodging a chase helicopter, he had no time to fully extend the landing gear. The result? A catastrophe. After hitting the runway at 217 miles per hour, his aircraft rolled 6 times, ripping itself apart. Although badly injured, Bruce Peterson survived to fly again, as did the M2. Using new data, it was rebuilt. Test pilot Bill Dana took the first flight in the M2F3.
I had the reward of flying the next flight after we rebuilt it with a modified aileron system that no longer had this lateral instability, and that probably was my most challenging flight because it followed immediately a stark disaster.
The M2F3 was modified with a third centrally mounted vertical fin to improve stability. In its 27 flights, it reached an altitude of over 71,500 feet and flew over 1,060 miles per hour. Retired in 1972, it is now displayed at the National Air and Space Museum in Washington, D.C. The vast testing facilities of NASA and other agencies have proved essential for successful research flight. This model of the HL-10, a lifting body stablemate of the M2F2, is being evaluated for different landing methods. Effort was even expended on tests for a water landing. Wind tunnel analysis was essential for any new aircraft, and exotic shapes like the HL-10 got a great deal of attention before flight test. Full-scale test models were expensive, but proved invaluable in discovering problems not noticed in the smaller scale models. Rolled out in 1966, its first glide flight exposed a desperate need for modifications. 1.5 years later, it was back in the air. The Northrop HL-10 was basically the M2F2 shape, but upside down. Instead of a curved bottom and flat top, it had a flat bottom. In October 1968, the HL-10 became the first lifting body to be flown under power. It would go on to make the first lifting body supersonic flight, eventually reaching 1,228 miles per hour and an altitude of over 90,000 feet. The unlikely-looking HL-10 would remain the fastest and highest flying of all the lifting bodies. The Northrop Northrop HL-10 and the M2 were true pioneers of the lifting body concept. NASA's Bill Dana flew them both.
Probably got less attention because they weren't ex-airplanes, but I considered them equally contributory to the lifting body technology and to the development of the steep power-off approach and landing techniques that were developed for the space shuttle.
The road to an X-series space plane has always been rocky. The Boeing X-20 Dinosaur was an early design for a reusable shuttle-type space vehicle that would enter orbit by multi-stage booster and glide back to Earth for a conventional horizontal landing. However, it became a victim of budget overruns and the swing toward the easier capsule method. But through its ancillary programs, much was learned. ASSET was an important X-20 support project designed to provide data on re-entry and test a number of shapes and heat-resistant materials. The small-scale models were launched on top of a Thor ballistic missile. The missile would almost push the little vehicle into orbit. After separation, it would glide down into the Pacific and be recovered. Recovery was important because although ASSET transmitted data, it also carried on board recording instruments. The recovered vehicles also vividly showed the extremes of heat encountered during re-entry and acceleration. Materials able to withstand such thermal punishment proved difficult to find.
But that was in the 60s, and there was a lot of metals that have been developed since then that people in those days were calling unobtainium because there just weren't any.
Another X-20 support program was the X-23, or Prime. Using a similar system to ASSET, Prime was designed to extend studies into wingless flight control during re-entry and test new kinds of shielding. Researchers developed a material that during extreme temperatures would ablate or char and peel off, taking the heat with it. The X-23 also tested a new lifting body shape that was set to make its debut as a manned aircraft. The Martin Marietta X-24A would begin where the X-23 left off, exploring the lower regions of the return from space. Rolled out in July 1967, it became a true ugly duckling story. For later in its life, it would go through a startling transformation. The X-24's appearance seemed almost comical, but its shape had purpose.
People called it the flying football, and it did look a little bit like a football, sort of partially deflated. But the object was to have a curved, smooth bottom on these things, because you would be re-entering bottom first, and therefore that's where you would have your ablative material that would have to withstand the heat of re-entry.
Jerry Gentry was the first to fly the X-24A. It called for skill and discipline.
Each mission, or flight test as we called it, was thoroughly rehearsed and practiced. In other words, I liken it to very much like a dance routine that somebody would do on a stage, because from the moment you launch, you're going through a set of procedures.
A series of unpowered glide flights began on April 17, 1969, with Gentry at the controls. This was common procedure with these air-launched X-planes, giving the pilot a chance to become familiar with the aircraft's basic handling qualities. Powered flights were initiated a year later in March. Again, Gentry was the pilot. Like its predecessors, the X-24A was powered by an XLR-11 rocket engine. which had a rather distinguished background.
The rocket engine was the same as the one that was used in the X-1 that when Chuck Yeager broke the speed of sound. It was slightly uprated and thrust, but other than that, it was identical.
After launch at 45,000 feet, the X-24A would fly under rocket power for around 2.5 minutes, then nose over for a steep 5-minute gliding descent. The pilot could almost just point at the spot he wanted to touch down on, as the angle of approach was so steep. After the fast-acting landing gear literally snapped into position, it would be traveling around 200 miles an hour. In an emergency, to give extra airspeed or to cushion the landing, small hydrogen peroxide rockets could be used. In over 3 years of flight testing, no major problems were encountered by the X-24A during these steep power-off landings. The method seemed to be a safe and economic way of bringing a space shuttle back to Earth without costly and heavy retractable landing engines that were being considered. Researchers saw other uses. Large commercial passenger aircraft use great amounts of fuel and create air and noise pollution using conventional landing patterns. The lifting body team offered a solution. To demonstrate, a big B-52 was readied for landing by bringing engines to idle and raising the large air brakes on top of the wings, dropping the flaps, and making an approach with landing gear fully extended. The effect was to cause greater drag, so the bomber would come in steep and quietly, effectively making a landing at a very low power setting and therefore becoming economical. Demonstrations were carried out for commercial aviation authorities using NASA's Convair 990 airliner with some modifications to its flaps. Although these spin-offs from the lifting body research program showed this was a viable, safe, and economic way to land commercial aircraft, the team came across no one willing to give it a try. The X-24A was to fly 28 times, reach a maximum altitude of over 71,400 feet, and chalk up a speed of just over 1,000 miles per hour. It was flown for the final time by NASA's John Mankey on June 4, 1971. But the story of this peculiar-looking aircraft doesn't end here, because the X-24A would be reborn. NASA and the Air Force were eager to test another shape that they felt could provide greater performance. Budgets were tight. To build a brand new aircraft would cost at least $5 million. For $1 million, they could reconfigure the X-24A. The already proven systems were retained, but a brand new body was fitted over the original airframe. The transformation took 10 months. The result was the sleek new X-24B. The new double delta flat iron shape was a stark contrast to the A model, and pilots that flew it noticed that its controllability and maneuverability was vastly improved. In 36 flights over 2 years, the X-24B provided a huge amount of valuable data. This sleek, futuristic design is seen as the final step in the evolutionary trail to the space shuttle. The shuttle's ability to return to Earth in a long, steep glide and touch down safely on a conventional runway is beholden to a family of the strangest shapes ever to become airborne. The X-24A's strange shape can still be seen at the Air Force Museum in Ohio, impersonated by its jet-powered brother, the never-flown SV-5J. It's a touch of irony, but a fitting tribute to the lifting body that had a facelift. The lifting bodies belie their odd appearance, for they proved vital for the continuation of aerospace advancements.
We were able to prove in the lifting body program that you could land these vehicles very, very accurately. Our touchdown dispersion seldom measured more than plus or minus 500 feet from an intended spot, and we always named our landing spot before we landed.
The X-24A and the other lifting bodies were a breed apart. Radical shapes, showing the way for future space flights, silently gliding home and landing safely. Even today, a scene like this seems almost unbelievable. A man floating in space while way below the world spins past. The trail of technology that allows us to experience such an amazing feat has its roots deeply embedded in the X-Plane series. By the end of the 50s, spaceflight was becoming a reality, and the Boeing X-20 concept seemed like the direction it was all heading. Powerful multi-stage rockets would boost the X-20 into orbit. Re-entry and landing would be by unpowered glide. During World War II, German researchers proposed a bomber using this boost glide system. It would skip across the upper atmosphere at 13,000 miles per hour. The X-20's proposed use of this dynamic soaring gave it a foreboding name: the dinosaur. In 1961, research was well underway. Thermal experiments were essential. The dinosaur would need to withstand incredible extremes of heat and cold. Technology was at its limits as researchers simulated speeds nearing 17,000 miles per hour. Although scheduled for flight in 1965, the dinosaur, like its namesake, was headed for extinction. A program that promised a pilotable, reusable spacecraft almost 20 years before the shuttle was canceled in 1963. The U.S. was taking the most expedient way to reach space. Expendable rockets and space capsules were a faster answer to the Soviets' early space race lead. The X-20's slower development and high cost couldn't compete with the quick and easy capsule method. As the space race drew closer to putting a man on the moon, researchers still worked at perfecting shapes that could conceivably fly to space and back. Launched from a helicopter, the Hyper 3 was a half-scale glider, built to test ideas a generation beyond the ill-fated dinosaur. It was piloted remotely from a ground-based simulated cockpit. The Hyper 3's specially shaped body provided all its lift. Small, straight, retractable winglets allowed lower speed landings. This lifting body configuration was projected as the shape of the space plane of the future. In the late 60s, the Martin Marietta X-24A, along with other lifting body aircraft, helped develop many aspects of flight without wings, including safe, steep approach landing methods crucial to the success of this kind of aircraft. In June 1971, the X-24A was retired, but researchers were still eager to investigate other configurations. As the glamorous Apollo missions drained cash flow, budgets were tight, So plans were drawn up to glove the existing airframe with a dramatically different shape. Jerry Gentry flew the X-24A for the Air Force.
In essence, they just changed the bottom of it from essentially an oval shape and made it into a very slender delta. And so they were able, at minimal expense, to look at two different configurations rather inexpensively.
The idea was to retain the existing and already proven systems of the old aircraft and fit a brand new body around it. The Flying Potato would be transformed into a sleek Flying Dagger. The new shape was a blended body and wing, aesthetically far removed from its previous form. Stunningly transformed, the new X-24B rolled out of Martin Marietta's Denver facility on October 11, 1972, 10 months after the A-model shell was delivered. Extensively modified, it had grown 15 feet longer. Its flat iron shape, exhaustively tested in wind tunnels, promised excellent handling qualities. It certainly looked like the shape of the future. The X-24B was designed to be air-launched. Modified B-52 bombers used for the X-15 were pressed into service. As a cost-cutting measure, the X-15 mounting pylon was modified with an adapter for the X-24. NASA test pilot John Mankey had flown the X-24A. On November 15, 1973, he would become the first to fly the new configuration under power. His observations would prove invaluable in comparing the two shapes' performance and handling qualities. The rocket power plant was the same trusty XLR-11 type that had pushed the X-1 through the sound barrier 26 years before. The handling qualities of the X-24B were very much to the pilot's liking. The double delta shape gave 2 times the lift and 3 times the maneuverability of the old configuration. The feel was more like a fighter, more responsive and flyable than the pure lifting body of the X-24A. The X-24B's most striking feature, its long pointed nose, was designed for a very good reason. It was found that the rounded stubby nose of the earlier form, although desirable to combat re-entry heating, was a handicap at lower speeds. With its sharp triangular form, the B model allowed much better handling and stability during its steep landing approach. By August 1975, the Space Shuttle project was well underway, drawing many ideas from the X-24B. The huge flat dry lake runways at Edwards were invaluable, but the shuttle needed verification that the proposed steep power-off landing method could be accomplished on a conventional runway. The X-24B showed that it could make accurate and safe landings on concrete. NASA pilot Bill Dana flew most of the lifting bodies and was a veteran of the pioneering X-15 project that had taken man higher and faster than any winged aircraft. He found the X-24B different in many ways, but familiar in others.
It was a very benign flight compared to an X-15 flight, but the approach and landing were identical in the two airplanes. A steep power-off landing with the landing gear coming down very late in the flight. And in that aspect, why the X-24 was very similar to the X-15.
Dana's first X-24B flight had taken place early in September 1975. The little craft had easily pushed up to Mach 1.5 and reached 71,000 feet. By that time, the 24B had already proved itself a much greater performer than the X-24A. In May 1975, John Mankey had taken the X-24B to its highest altitude of 74,130 feet. The previous year, U.S. Air Force pilot Colonel Michael Love had clocked a speed of Mach 1.76, or 1,163 miles per hour. Bill Dana's second flight was the X-24B's final powered flight. As the XLR-11 rocket engine shut down, Dana had just pushed the little bird into supersonic flight. At a conservative altitude of around 57,000 feet, he prepared for the fast glide down with the familiar steep landing approach. This method of landing had proved very efficient and accurate. The pilot almost had only to point the aircraft at the spot where he wanted to touch down on. When activated, the X-24B's rugged landing gear snapped out amazingly fast. The pilot would wait for the last possible moment to drop the gear, as the drag caused loss of precious speed, lift, and control. Power-off landings left no second chances.
I think the major contribution of the lifting bodies to technology to date has been the demonstration that a variety of various shapes could be landed power off, even though they had steep final approach glides.
The X-24B's final powered flight in September 1975 also marked the final rocket flight of the X-plane series. Ironically, it operated with the same type of engine used on the first X-plane. The Martin Marietta X-24B is now on display at the United States Air Force Museum in Dayton, Ohio. The most advanced of the lifting bodies retired as the space shuttle was being readied for its debut. The evolutionary trail towards the shuttle was completed by this truly unique aircraft.
The original space shuttle intended to carry 4 or 5 jet engines and extend them after re-entry, light them up, and then make a power-on landing. And through our experiences with the lifting bodies and our ability to successfully land power off a number of different shapes, we convinced NASA Houston to remove the landing engines and the jet fuel from the space shuttle. This reduced the orbital weight of the shuttle 35,000 pounds and reduced the launch weight by 1 million pounds.
The orbiting shuttle is in some way the realization of the X-20 dinosaur. Boosted into orbit like the Apollo capsules by jettisoned rockets, the shuttle is a pilotable, reusable system. Thanks to the invaluable data provided by the lifting bodies, it can make a controlled gliding re-entry and descend to a safe pinpoint landing anywhere on Earth. However, the lifting bodies may still have a lot to offer the next step beyond the shuttle. The future of the X-planes looks exhilarating. These computer images are of the shockwave pattern around the X-30, the proposed NASP or National Aerospace plane. Designers use supercomputers to provide data that wind tunnels can't give us. This part airplane, part spaceship will need to fly over 17,000 miles per hour and survive the tremendous heat loads of accelerating into orbit and re-entry. New materials with greater heat resistance, lighter weight, And greater strength will also need to survive the extremes of ultra-cold. New alloys and carbon fabrication technologies will be stretched to the limits. With all this information from simulation and supercomputers, we know pretty much what to expect, so why should we build the X-30? Scott Crossfield, X-plane test pilot and aerodynamicist.
If you could do things with unmanned systems, with computers, you might just calculate what you want to do and not bother to build the system. This is a human experience, this thing of being on Earth. The Russians saw the backside of the moon first, but we had a man on there first. And the strides that we took in the technology of understanding the moon are orders of magnitude more than they learned just by flying around the backside of it, huh? Or with the unmanned systems that land on the moon.
NASA and the Department of Defense have been exploring hypersonic technologies for years. Each X-plane can almost be seen as a building block of knowledge working towards the X-30. The National Aerospace Plane will be a single stage-to-orbit space vehicle, able to take off under its own power and fly into orbit around the Earth. After completing its space mission, the X-30, like the shuttle, will make a long, unpowered, gliding descent, re-enter the atmosphere, and land on a conventional runway. Jay Miller, aviation historian.
In effect, the NASP is point A. It is a research tool. It is an exploratory tool. It is hardware that will allow us to prove whether or not we can build a vehicle that will basically be single stage to orbit.
The X-30's flight tests will be in carefully monitored increments, adding speed a little at a time. Computers will use this data to stay ahead of the game, searching for hot spots on the X-30's skin that, if not discovered, could eat up the plane during hypersonic flight. Many of the lessons learned from the X-15 and lifting body programs about aerodynamic heating, shockwave patterns, and countless other subjects form the huge database that researchers refer to. The National Aerospace Plane Project stands on the shoulders of its pioneering X-plane predecessors. After many years, they continue to yield priceless information, even of a more down-to-earth nature.
There's no question that the National Aerospace Plane will use techniques developed to land the X-15 and to land the lifting bodies when they're learning how to set up their approach pattern for the X-30.
Originally conceived as a Concorde-like sleek space shuttle, now as the X-30 takes shape, it seems to be a much more radical design. Maybe the lifting body has found its time. Jerry Gentry, lifting body test pilot.
The lifting body program, people lost obvious interest in that when the decision was made on the space shuttle configuration. A great many people thought at one time or another that the lifting body would probably be the configuration for the space shuttle. What's interesting is to see now what the configuration is for the National Aerospace Plane, or X-30, and indeed it is a lifting body again. So the lifting body is starting to return to vogue or popularity.
The affirmation of the lifting body shows how so much high-technology research is a matter of planting the seed of an idea and many years later seeing it bear fruit. Such a huge project could never be attempted by one company. The National Aerospace Plane will involve 5 major aerospace companies in a huge consortium effort controlled by NASA and the Department of Defense.
The difficulty lies that when you're trying to build a single stage to orbit vehicle, you're looking at a very expensive platform, particularly when you're talking about a limited production vehicle. I mean, they're not going to build but maybe 2 or 3 of these aircraft. And they are strictly research vehicles to prove certain points, to achieve certain performance objectives.
But the scramjet power plant has yet to be invented. Just to start one up would be like lighting a match in a hurricane.
The scramjet is kind of the next generation, if you will, of propulsion systems. It is kind of the ultimate jet engine.
Like all X-planes, the X-30 will tackle seemingly insurmountable problems and open new doors. Scott Crossfield, involved with X-planes from the X-1 to the X-15 and now the X-30, is still a great believer in the research airplane.
I'm determined we're going to catch up with where we left off on the X-15 with the National Aerospace Plane. The limitations being largely economic. It's not technical. We know more about the National Aerospace Plane today than we did at the Apollo, the X-15, the Mercury at this stage. So that's my thesis. And it's a natural extension of what's proven successful, the research airplane program.
The promise of the X-30 National Aerospace Plane is viewed as the ultimate X-plane. The payoff will be just like the other projects, new ways of flying, building, and powering the next generation of flying machines. The dreams that were stirred in the heady days after World War II as the X-1 flew into supersonic flight for the first time are still alive. But there can be no ultimate X-plane, as there will always be another goal to reach, another door to open, and another X-plane to fly into the unknown.